This presentation is about data hiding. This week's entire lesson is about data hiding and the techniques. This presentation is meant to accompany the course CGS 5131 at University of Central Florida. My name is Rick Lineker. Here are the objectives for this week. We'll start by just taking a look at why data hiding is important for both the bad guys and the forensics investigators. We'll talk about file data hiding. Now, we've already sort of mentioned that when we looked at concatenating images, but we'll spend a little more time on that topic. From there, we'll go to disk slack data hiding. Disk slack is the sectors on your disk that are not allocated. Okay, so for this section, we're going to be looking for unallocated disk sectors into which we can insert our data. File slack, however, is different than disk slack. While disk slack is a bunch of unallocated sectors, file slack is where we put data into allocated sectors, but they're the slack at the end of a file that's not used. And I will talk about that in much more detail. From there, we'll go into encryption. Now, I don't spend a lot of time on sort of the nuts and bolts of encryption, just because we do that next semester in 6418. We really sort of get into the mechanics of encryption. Here, we're just going to be showing how to encrypt and use that for data hiding. After that, we spend a good bit of time on steganography, and more specifically, we're going to talk about image steganography. Now, when we talked about images, and when we talked about images in the data carving section, I spent a good bit of time talking about how images are laid out in the architecture of images. So we're going to kind of review that, because that turns out to be really important for the topic of image steganography. There's other steganography we'll talk about too, and we'll sort of allude to that, maybe give a few examples. And lastly, we're going to take the subject of file slack data hiding and revisit it and talk about how forensics investigators can actually do a comparison of the entropy of file slack and the entropy of the file data itself. And in this way, they can sort of make a match between slack space that really doesn't belong to the file. But if you use steganography, there's a way that you can take the original file data and steganographically hide the data within it, not to write back to the original data, but then take that data and put it in the slack space. And we'll talk a good bit about that. So why is data hiding important? Well, if an investigator doesn't know that data is there, then encryption or obfuscation or whatever, we've already talked about both of those, doesn't even matter, because it can easily be missed. And many times, once data is hidden, especially if it's carefully hidden and expertly hidden, it prevents casual inspection, such as doing a directory or something. It prevents casual inspection from discovering the hidden data. So this is a really excellent way to put data somewhere where nobody's going to even know it's there. It does make data recovery of stuff that's hard. Now, next week we do recovery of deleted files. Well, this is better than even deleted files, because deleted files can be most of the time recovered. But if the data is hidden, a lot of times there's no way you can even get it back, because you don't know where it is. So what types of data can you hide, or should you hide, or what types of data are people hiding today? Well, there's no definitive list, because it can be really anything that can be imagined. Some of the things I've seen are as follows. Secret information. This is a real interesting thing. This has a lot to do with, say, industrial espionage. I've worked on cases where employees within a company were actually hiding data that was company intellectual property in order to sneak it out. And the reason they do that is either they're competitors, or they're selling to competitors, or they're disgruntled and they want to do some damage to the company. So secret information is really common to hide. Secret information also might be, say, credit card lists of credit cards, or even just one credit card. You know, sometimes we think of hidden data as being this big voluminous set of information. A single credit card, along with its expiration and code, is going to be like 22 bytes. So you don't need a lot of space to hide really useful and valuable information. Passwords can be hidden. For instance, you might know what a password is, and you might want to hide it so someone coming behind you knows where to look for it. Or you might have a list of passwords, your passwords, and you might say have a list of 20 or 30 passwords and put them into some sort of hidden area. Maybe the secret formula is some scientific invention or something. I know I've had software inventions, and they didn't necessarily have formulas, but they had short pseudocode and short code snippets that I had to protect. And so you could hide similar data, and that way people can't find it very easily. Plans for like bombs, plans for nuclear rockets, plans for whatever. Maybe plans for, say, some illegal thing that you're planning, some conspiracy that you and a group of people are planning, and you hide the data so that everybody in the group knows where to find it and can sort of participate in the plans, either read the current plans or maybe amend them, but nobody else knows where the data is, so they're not privileged to the plans. Messages, for instance, if you do steganography on an image, you could actually post it to a website, and then someone could just visit your website, do a right click and copy the image, and extract the steganographically hidden message from within the image. And we definitely cover that in this section. Contraband. Contraband would be things like maybe a link to that Silk Road, or most commonly we think of contraband as, say, like child porn or something that's illegal. So you can hide that somewhere. Obviously, people who have it are going to want to hide it. And finally, malware can be hidden and is normally hidden. That way your operating system or your antivirus or your anti-spyware isn't going to necessarily find it. This is just sort of a high-level view of the types of data that get hidden. There are lots more, and I do encourage you to talk about other types of data in the forum this week. Okay, so let's talk about data hiding with a really, really simple technique. However, it's a simple technique that is still many times overlooked. And we've already done this, so this won't be new for you. This will just be a review. So I've got 5 files here, and I am going to append data to these files in order to hide it. For instance, if I say copy /b, and /b means binary. Otherwise, if you don't use the binary, you run into an issue that potentially 2 bytes, 13 and 10, could be misinterpreted. So I'm going to say main menu.bmp plus doi.txt. Okay, and those are the source files. And so it's going to put main menu.bmp first, and then it will append doi to it. DOI is Declaration of Independence. And now we're going to say new file.bmp, and we're going to make sure we keep that BMP extension, because that way the operating system or any kind of programs that open it will know what it is. Okay. So now we have this new file.bmp. Okay, so here I've got my folder, and you can see that Windows thinks that new file.bmp is just simply a BMP file. And if I double click, I should get a file viewer to display it. There you go. Okay, you've seen that picture before. It has no idea that the Declaration of Independence is appended to the end of that file. So that's a really safe way to hide data. So let's go ahead and open that up in WinHex. Everything looks normal here, no problems there. But if we go ahead and go to the end of this file, you can obviously see that this is not BMP data. This is text data. Here's binary data, so the BMP actually ends here. Remember, a TXT file does not have any kind of a header or signature or anything like that. So the only way you can really know that it's a TXT file is just that it's text data. So I can actually data carve this, which you're already really good at. Mark the beginning, mark the end, and now go to Edit, Copy Block, into New File, Carved Text.txt, and there we go. So once again, this is nothing new, but I'm talking to you, I'm presenting this in the context of data hiding. But it gets a little more convoluted when we do it the opposite way. For instance, I could try this. I could say doi.txt plus main menu.bmp to new file 2.txt. Okay, and that actually worked. My go-to program for viewing TXT files is Notepad. So new file 2.txt. It's taking a while because the BMP is actually so large. It's 5 megs. Notepad is actually not very good at viewing binary data. Okay, so this looks really perfectly normal. Remember with the BMP viewer, it looked normal too. It just looked like a regular BMP file. So this also looks normal, looks like a normal TXT file. But as we scroll through it, you can see it's binary data, and you can even, if you're really paying attention, you can see it starts with BM, which obviously is a bitmap, but you might not notice it because that looks kind of like text, but you do notice that it's a lot of binary data. So the order in which you append these files is going to be really important. I wouldn't ever suggest appending anything to a TXT file because the data you append will be so transparent when you run Notepad or any other text viewer that it will almost be worthless to hide data like that. So with regard to hiding file data, when you hide file data using the append method, consider the following. You want to append to a file for which viewers always stop after the first file is interpreted. Remember, when we appended to a BMP file, the BMP viewers would they'd load in the BMP data and they'd stop right there because that's all they're really programmed to do. Don't append to something such as a TXT file where it's going to be totally obvious at the end of the text data that binary data follows. Another example of this would be, say, a .csv file or anything that's going to be like totally transparent that you've appended binary data. When you do look for hidden files, you need to really check for 2 things. First, you need to check for file signatures such as PNG, GIF89A, BM, and so forth, JFIF. We've already talked about that. You also need to take a look and see that data is either characteristic or uncharacteristic. Remember when we appended a BMP to a text file, we eventually got to a point where it was obvious that it was binary data. Or when we did the reverse, when we appended a text file to a BMP, at a certain point it was obvious that there was text data there and not binary BMP data. So now let's talk about hiding some pretty simple data within image files. And image files actually contain metadata called EXIF, E-X-I-F. So if you right-click on an image and you go to details, you actually can see that. This title and subject have been set. This is a mountain. Comments, I love UCF. Authors, Rick Lineker, copyright, and so forth. Okay, so this is metadata that is contained within this JPEG file. Now you could actually go and use WinHex to edit the metadata in a file. However, it's a very dangerous thing to do because when a JPEG file is saved, if there's nothing in one of these fields, it doesn't save space for it. So you could actually end up really messing up the JPEG file if you use WinHex to edit these. Now, obviously, you can go and edit a string like that with WinHex, but you couldn't say add say tags here. You would definitely end up messing up your JPEG file. Okay, so there is a way to do this pretty easily. There is a website that you can go to, and if you just go to colorpilot.com/exif, exif.html, there's a free program that you can download that will allow you to edit EXIF data in PNG and JPEG files. Okay, so let's go ahead and run this program. Mountain.jpg, that's what I showed you, and remember we right-clicked on it, went to Properties, Details. So you see everything here, Artist, that's exactly what we saw here, but let's change the artist to Quasimodo, and I really love UCF. And this is a cool mountain view. Okay, we'll go ahead and save that. Okay, now let's go back to Properties, Details, and you can see that the EXIF data has been changed. So with that program, it was legally or safely able to edit the EXIF data. So this is a really nice way to hide data. I want to show you one more thing about the EXIF data, though, that would be really interesting. So here you can actually put GPS locations there. And obviously nobody thinks to look for GPS in an image, GPS locations that is. Okay, so the reason that these GPS locations are there is because from your phone or whatever, you might take a picture and you know, there might be some interest in saving the GPS location within the EXIF data. But let's say you had some buddies and you were involved in some sort of a conspiracy of some sort. So you could actually take a JPEG or a PNG and put GPS data in where your next meeting is going to be. And then you could actually go ahead and post it to the internet. And the information would be available to the entire world, but nobody would know to look for it. And then you could go here and say 2 p.m. is my, and then they would know to meet you at that GPS location at 2 p.m. So this could actually be a useful tool. So there's a really fairly easy and crude way to edit BMP files so that you can hide data in them. So here I've opened up a BMP file called mainmenu.pmp, and the blinking cursor is at the beginning of actual data. The bitmap file header and the bitmap information header, both of those together take up 54 bytes. So to find the actual data to actually find out where the data starts, you have to skip 54 bytes. But if I go ahead and click over here in the ASCII, you won't see much really. And please note that, let me go ahead and show you this image. Please note that this is a busy image. And one more technical detail is that BMP images, actually when they're stored on disk or in memory, they're actually reversed. So when we actually are starting at the beginning of the file, we're not really up here at the top, we're really up at the bottom. Okay? I know that's a weird thing. I don't know why they decided to store the data on disk upside down, but they did. When I first started decoding BMP files, many years ago, it took me a while to kind of come to grips with that and have all my code deal with it. Now it's automatic for me when I do BMP decoders. But now, one really interesting thing, notice down here at the bottom, everything's pretty much some sort of shade of blue. And another really interesting thing about BMP files, we normally think of pixels as being RGB. Okay, we think of the red channel the green channel and the blue channel. Here again, stored on disk, it's not that way. When it's stored on disk, it's actually BGR. It's stored in reverse order. How that happened over the years, I have no idea. It's probably some interesting story that has a lot of history. So now let's go back to WinHex. And if we take a look here, you'll notice, true enough, the blue value, remember it's not RGB, it's BGR. So this is the blue value. Skip to, that's green, red, blue value, green, red. And actually, so if I took over here and I went ahead into the ASCII and I said R, I, skip 3, let's see, here's 3, C, K, I just put my name in there, and I'm going to go ahead and save this, and let's go ahead and show that again, main menu.bmp, and you're never going to see it. You're never going to notice that those blue values were slightly different than the old blue values. In fact, I don't think I changed them more than 10 or 15. And we do steganography soon. Please don't confuse this with steganography because it is not steganography. However, it has similarities to steganography. This I would consider would be a very naive way of hiding data within the actual BMP data. If you had mostly red data, you would edit the red bytes. If you had mostly green data, you would edit the green bytes. You might have some sort of grayscale where you can edit all three, or something similar to grayscale, or brighter like whites. But it's safe down here to go ahead and edit the blue values. So this morning I went on a long walk, as I normally do in the morning, and while I was thinking about this class and data hiding, I came up with a new method of hiding data within BMP files that's fairly robust. So I came home and wrote a proof of concept program, and lo and behold, it worked just fine. So now I'm going to share that with you in this class, and who knows, maybe it'll turn into something really good. So this is a novel way of editing BMP files to embed information in them. And here again, as with the things before, you can actually use the BMP for editing and convert it to a PNG file. Okay, suppose that you have an image with relatively full colors and an image that's fairly busy. The only reason that these two things are desirable is because full colors give you lots of room to play where people aren't necessarily going to see the changes you made. And a busy picture is actually going to also make it unobvious, make it much more easy to hide data that you've inserted. So if we showed before, when a color channel has a value close to ASCII values, you can usually change them and not notice a difference. Remember what we did before when we did that really naive BMP editing. So the first thing we have to do is we're going to consider groups of pixels. Before we were just editing the blue values, okay? And that's a pretty simple and, as we already said, naive way to do things. But in order to adjust the data so that there's less of a change for each color channel or each pixel, what we want to do is we want to use groups of pixels, not a single pixel or not a single color channel. So what we're going to do is we're going to choose a number of pixels and then multiply that by 3, and that's how many bytes we have to work with. Okay, so for this example, we're going to use 4 pixels or 12 bytes. Now, I would definitely not suggest that you hard code that into a program, because as soon as you do that and people know, or people are used to 4 pixels, 12 bytes, then it's a lot easier to go ahead and decode it. So what you want to do is make sure that that's a variable amount. Now, in my example, it's hard coded in terms of defines, but it's just a proof of concept program. So just make sure that those two values would vary. So now suppose we have a message to hide. For this programming example, the message is my name is Rick Lineker. It's just an ASCII string. It could be any string, and could be any sort of buffer of symbols. This supposes all of our messages are going to be in terms of bytes. So for each symbol in the message, we do the following. So we get a total of the data. So for my programming examples, we're going to total up the 4 pixels or 12 bytes. Now I have group size defined as 12, but it can be anything. For this example, it's 4 pixels and 3 color channels, totaling 12. So here you can see how I just get a total for the data in the group, and now I've got that total. I actually created a function in my programming example, so this is just kind of an example of what I did. So we have to select a mod number, and this mod number, what we're going to do is we're going to take our total and mod it with this mod number. And that is going to be kind of our target character, and we'll talk about that in just a minute. I know that might not make a lot of sense, but it will shortly. Here again, I would not hard code the number, although my programming proof of concept example is hard coded. If everybody knows that if everybody knows the value of that mod number, then it's going to be really easy to sort of get in there and detect the message. So for my example, I used 127, and the reason I picked that was because it was right there between 0 and 255. I could have picked like 128 or 126, but I just picked 127. And I think the real reason I picked that was because it's at the top of the ASCII value range, and the messages I plan to hide for this proof of concept were all going to be ASCII messages. So that would actually give me so that would actually make things sort of come together a little bit faster. If you had the full range from 0 to 255, say for some binary data, you might pick something a little bit higher. So the goal is to have the total for the group size data when modded with the mod number equal to the next message character. Okay, let's say my total is 1,000. 1,000 modded by 127. You would get the value for that, and let's go ahead. Okay, so let's say 1,000 mod 127 is 111. Okay, that's an uppercase letter. And that may or may not be what we're looking for, but what we're trying to do is get that number to match what the next character in our message is. Okay, so here's the code, or it's not really the full code, it's the pseudo code for what I just described to you. So we have this J number, and the reason we have J number is we could, inside of this while loop, we could have a for loop that counted from 0 to group size. However, we might have to go more than that. We might have to go more than 12. We might have to continue to adjust each one. So the first time through, we might add one to each byte, then we might add another to each byte. We do that until we get to where the mod value is correct. So I had this get total function, and get total just takes the data and gets the total of whatever that group size is, in this case 12, mods it with a mod value, and we check to see if it's equal to the next message character. If it isn't, we keep doing this. If it's equal, then we bail out. So here I have a method adjust data, which I actually don't have in the real program, but just to keep things simple. Then I increment my J variable, so I go to the next one. Notice I'm doing data sub J mod group size. That way I always keep in the range of 0 to 11, 0 to 11. No matter how many J's I iterate to, I still have values of 0 to 11. So now we're going to take a look at the source code and run through the actual nitty-gritty. Here is my source code. It's a C++ program written in Visual Studio 2013. And I'm going to go through and explain it to you, and then I'll go through and run it in the debugger. Okay, so group size is 12. That's 4 pixels times 3 color channels. Here again, this is the define, which means it's hard-coded, but it should not be. Mod number is 127, and I just define that for convenience. So here's my count total function. It takes a pointer to whatever the next group chunk is going to be. In this case, it'll be 12 bytes. sets total 0, and loops through and adds everything up, returns the total. So that's just a matter of convenience because I use it a couple of times. It's actually a really bad idea. I've got a BMP file hard-coded, but I wanted to make this program as easy to create as possible. So I did that, I hard-coded that, but you really need some sort of command line parameters or maybe a file selector or something. So I get the file length, allocate the buffer, read the data, and close the file. Oops. So there we go. Now I have my message, and as an explanation, there are 2 blank bytes here that are not actually part of the message. Here is the dilemma. You can decode a message, but a BMP file is going to be a lot longer than the message is. So then you'll go on and on and on to the end of the BMP file trying to decode a message. So I left these 2 bytes here so I could put the message size in. Now, for a real program, what I would do is I would make this like that, and I'd do a sprintf message to store %05u, so it would be padded with this 5. So that would actually store it. That would be big enough to accommodate almost every message we'd be using. But I didn't do that. I just sort of shortcut this so that I only have 2 blank spaces there. But here I actually filled in the blank spaces with ASCII values for the string length, and I think it's 27. I'm pretty sure it is. Okay, so the point of all this is, I should actually put this up here and organize this program a little better. Oops. The point of all this is that in the first part of the message, I actually need to have the length of the message, because otherwise when you go to extract the message, you'll never know. Okay, here's my data pointer. Now I loaded in a BMP file, and remember that a BMP file has 2 data structures at the beginning. One is the bitmap file header, and the other is the bitmap info header. And altogether those are 54 bytes. But rather than hard coding 54 bytes, I went ahead and let the compiler do it for me, and I added the size of both of those. That's actually a better programming pattern than putting 54 in there, even though it's always going to be the same. So when it compiles, it'll compile to sub 54. However, it's just easier to read, so people who come behind you know what the meaning of the 54 is. So now I start at the beginning of the message. Now bear in mind, even though those first 2 bytes are just size, I still need to encode those into the data. Okay, I call my method to count up the total in this particular chunk. Now I'm going to start my data direction, meaning I'm going to add to all bytes at 1 just by default. And what I want to do is I want to make sure that for brighter pixels I'm going to add, because it won't be noticed as much. If you brighten in the midst of other bright pixels, it won't be noticed as much. However, if you have darker pixels and you dim, it won't be noticed as much. This is a safety though, because there's a possibility that the pixels can be so bright that you don't have enough room, and you'll ceiling out at 255, and then you'll get stuck in the while loop. If I'm less than halfway, and also here's just a check just to make sure that here again I could bottom out and get stuck in the while loop. So my direction is -1 there. Okay, so that means I'll be subtracting instead of adding. So while my total mod the mod number, remember we said we're going to take whatever our total was and mod it with a mod number, while it doesn't equal the message to store, I am going to adjust the data. Okay, my delta direction is greater than 1, that means I'm going to add. So I got to make sure I don't exceed 255. So I add to the data itself and I add to the total. Otherwise I'm going to subtract, making sure that I'm not at rock bottom. I subtract and I subtract. Okay, J++, I go to the next in the group, and notice I'm doing J mod group size, so I never get past 0 through 11. 11 would be the highest value. Then I go to the next group of pixels, which is the group size of bytes for the next round. So that's all that's involved in inserting the message data into the BMP data. So now what we're going to do is we're going to test it. We're going to test to make sure we got it right. So here's a local buffer. We point back to the beginning of the BMP file. We count the total. And the total modded, the mod number should be the first character. Okay. Go to the next group. Count up the total. Here again. So that should be 27. 2 and 7 because that was the size. Okay. Create this for the retrieve message. So we're going to go through the size, and we could actually take the string length of the message to encode, but we take the integer value of that ASCII character set. So for each character, we count the total, go to the next group, and we put the modded value into the retrieve message. And this is just null terminating it each time. We print it out, and here I've gone ahead and written this BMP out just to show you that the quality, perceived quality, is no different. Let me just show you the original main menu. Okay, main menu 2. You can't tell the difference. Okay, so let us use the debugger and walk through this program. And here I have my breakpoint set. Let's see what it sets the first 2 bytes here. Okay, you'll see it says 27. My name is Rick Lineker. So 27 is the length of the string, and that, by the way, includes the two size bytes. Point to the beginning of the BMP data. Now what we're going to do is we're going to walk through the string, the message string. It should count the total. Total's going to be a fairly big number, 220. But here we calculate the direction. We adjust the data. That's pretty long. Let me just set a breakpoint. Let me set a breakpoint here. Yeah, there's already a breakpoint. Okay. Okay, so now inside of the BMP, we've encoded or hidden our message. So now what we're going to do is sort of reverse process and just make sure we got it right. Okay, point back to the beginning of the BMP data. Okay, count the total. Now this size sub 0 should be 2, and it is. Okay, it's actually a lot easier to decode than to encode, right? Size sub 1 should be 7. Now we actually have to null terminate the string, so we put a 0 there. So now 27, what we're going to do is we're going to loop through -2 because we don't have to, we've already got the first 2 bytes, so we don't need to worry about that. So we loop through, and I'm actually going to go ahead and set a breakpoint here so we can go through a few iterations. So let's see, continue, continue, continue. So far in retrieve message we have my blank space, continue, continue, and so forth. Let me get rid of that breakpoint. And there's another breakpoint I'll skip to. And there we go, retrieve message. My name is Rick Lineker. So that's all there is to it. So I am actively looking for some help to work on a project. In fact, you just looked at the project that I'd like to develop. I think since it's such a new and novel idea, it's probably worthy of an academic peer-reviewed article. So I am planning to write a peer-reviewed academic article on the previously demonstrated methodology for data hiding. It is kind of a big job to do that, and I know a lot of you are looking for extra credit and would like to sort of be involved in something. So what I'm asking for is your help with any of the following, and I can use the help of one person or 10 people or 20 people. It's fine if I have a lot of people, it's fine if I only have a couple. But here's what I need help with. So the code testing and cleanup and commenting, and you know, you just need to go, someone would just need to go through and test the code under different situations with different files and stuff, different BMP files, different messages. Maybe create something where, you know, stuff isn't hard coded, and it could take some command line parameters to set, say, the mod value and the group size and the file name and the message. Of course, the message should actually either be something in quotes from the command line or maybe a text file with the message. Then I need someone to do research and just look up in amongst the other academic journals and just see if there's anything similar, or, you know, just see what's out there. I need someone to create charts and graphs. So these journal articles always look a lot better, and the charts and graphs actually break stuff up. So maybe taking Visio and making sort of maybe UML diagrams for the process, or even just flowcharts or something would be fine. Then someone needs to look for the right journal to submit this to. There are lots of academic peer-reviewed journals. What we'd want to do is submit to the correct one so we have a better chance of getting accepted. And I need someone to do editing on the article. I'm planning to write the article myself, but I need someone to kind of do a technical edit and someone to do a grammar edit also. Now, I can pay to have a grammar edit done, but the more you get done in advance, the better off you are. And then there might be other things that I haven't even thought of yet. So if you're interested in any of the following, what I'd like for you to do is send an email to my UCF address and just let me know which of those you're interested in. And another thing, go ahead and tell me when you're available for meeting, because somewhere along the way we'll have to meet as a group, and then I'll try to put it together in a week or so. And I think the goal would be to have this submitted by Thanksgiving. So we're not in a big, huge rush, but at least that gives us kind of a goal to have in mind. Then your names will get added to the article byline. So this could actually really be a tremendous boost for you if you're going into academia, or just even as a resume item.